Welcome back. Actually, before I teach you how to figure out how high the ball went, and you might already be able to figure it out, I want to show you really kind of a more intuitive way for figuring out how fast the ball went. I used the equation this first time just to really show you that this equation can be useful. But I personally always forget equations, so I find it very useful to have kind of a common sense way of figuring it out as well. And really, this equation was derived by coming up with a common sense way. But I don't know if that last statement made sense. But anyway, let's move on. So let's say that same problem, but let's just think about it without our equations, because that's always a good fallback when you're panicking in the middle of an exam and you can't remember if an equation had a 1/2 or a 2 or a minus or a plus or t squared. And so it's good just to think about what's happening. So when I throw a ball straight up, I have let's say it's a baseball. It looks like a baseball. And I throw it straight up where, my velocity, velocity initial is equal to, well, I throw it up with let's say that this is the variable. This is my initial velocity, v sub I, right? What's going to happen? As soon as I throw it up, it's going to start decelerating, right? Because I have the force of gravity decelerating it immediately. So gravity, we're saying minus 10 meters per second squared, right? So this ball is going to keep decelerating until its velocity goes to 0, right? The ball, if we were to graph time and distance, where this is time and then this is distance, right? At time 0, we're on the ground, and the ball, it starts off going really fast, but then it starts slowing down, and then its velocity goes to 0, and then it starts accelerating in the negative direction, starts going fast, comes in, bam, and hits the ground again. So what happens is the ball starts fast, starts going slower, 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 until its velocity is 0, and then it starts you could either call it, you could say reaccelerating in the opposite direction, or decelerating really, but reaccelerating in the opposite direction, and then it hits the ground. And actually, we know, not assuming nothing about air resistance, et cetera, that the velocity that it hits the ground with is the same velocity that it left your hand with, just in the opposite direction. So there's a couple of interesting things here. The time at which its velocity is at 0, so that point right there, that's going to be at t equals 2, right? And we know that this shape is actually a parabola, if you remember that from Algebra 2. Why is that a parabola? Well, what was the equation for? Well, we figured out the equation using that previous formula. I don't want to use it this time, but what was that previous formula? It was change in distance is equal to vi t plus at squared over 2. So it's a parabola. But I think if you had thought about it, you would have realized also it's a parabola, right? And it points downward because a is negative. So the t squared term is negative. So that's why it opens to the downward side. So I think that might make a little sense to you. So what we could figure out is, if we're given a t, we could say, well, half of that number is, let's say that t equals 10 seconds. T equals 10 seconds. So we know that in 10 seconds the ball left my hand, went up some distance, and then came back down and hit the ground. What we also know then, though, is that t over 2 at 5 seconds, the ball was essentially stationary for just a moment. Its velocity it decelerated, hit 0, and then right before it started reaccelerating again, or reaccelerating downwards, its velocity was 0 at the time t equals 0. So what can we use, that the fact that the ball decelerated from my initial velocity to 0 in 5 seconds? What does that tell us? Well, we have the very simple equation, change in velocity is equal to acceleration times time, right? That's you probably knew that before watching any of these videos. And the change in the acceleration, well, that's just the final velocity minus the initial velocity is equal to the acceleration times time. In this situation, what's the final velocity? Remember, we're not going to go all the way to here. We're just figuring out from here to time equals 2, right? So what's the final velocity? Well, we're saying that point where the ball it's not going up, it's not going down. So its final velocity is 0. So 0 minus initial velocity is equal to acceleration. Acceleration is the acceleration of gravity. Minus 10 meters per second squared. And then the time is, if this is, I know it's a little confusing because I'm using the same t, but let's say that this time is, I don't know, t sub 0, just to kind of make sure it's, it's not a variable, it's actual time. So this is t sub naught over 2, right? Because the ball is motionless right at the peak of its, well, we're not an arc because we didn't throw it in, but right at the peak of its travel. So it's acceleration times time, but at this time the time is going to be t sub naught over 2 times t sub naught over 2, right? So once again, we have, if we, let's see, we can, the 0 doesn't matter. We can multiply both sides times -1. We get plus vi. And we get vi is equal to 10 divided by 2, 5 meters per second squared t sub naught, which was exactly what we got in the previous video when we used this formula. And I think it makes sense to you that hopefully this was kind of an intuitive way of thinking about what happened. And before actually I do the distance, I actually want to graph what's happening because I think it just dawned on me that that might be something that will give you more intuition. I'm all about giving you intuition, so you never forget this stuff. Just as, so this is, if we were to graph, that's an ugly looking axis, but I think you'll get the point. This is distance, this is time. We already said it's going to be like a parabola, like that, right? Where, this is t sub naught over 2, this is t sub naught, right? It launches really fast, and then it slows down, and then it's motionless right here, and then it starts reaccelerating downwards. So if that's the distance, what does the velocity graph look like? Well, the velocity graph, I'll draw it right below. I'll draw it in another color just for variety. That's a bold. So over, actually, no, that's not how I want to draw it. I have to draw the negative side too. So this is time, and then this axis is velocity. So I actually have the so we start off at a positive velocity, right? We start off at v sub I. And what's going to happen here is the velocity decreases at a constant rate, right? And that rate is just the rate of acceleration. The velocity decreases until at t sub naught, let's see, at t sub naught, let me switch back to yellow. At t sub naught, oh, whoops, I'm using the wrong tool. It actually looked like I was drawing something. At t sub naught, the velocity now is negative vi, right? Remember we said when the ball comes back down, it's going at the same velocity, just at the opposite direction. So this point right here, which is t sub naught over 2, that corresponds to this point, right? Which makes sense, because that's the point at which the ball has no velocity. And look, the velocity is 0. So the ball starts going up really fast, slows down at a constant rate, and what is the slope of this line? Well, the slope is just the acceleration, right? Because velocity is the acceleration times time. And then it's stationary for just a moment because its velocity is 0. And then it starts accelerating, or you could say decelerating or accelerating in the negative direction until the point that it's going at v sub I down. And of course, if you were to graph acceleration, if I were to graph acceleration over time, acceleration is time, acceleration. Acceleration is constant. It's right here. Let me just get a line tool. The acceleration is just a constant minus 10 meters per second. So it's going to look like that. And it's just the slope of this line. And if you know calculus, it'll make sense to you that this line is the derivative of this line, or this curve. This line is the derivative of this curve. And even if you don't know calculus, I think it makes sense to you that this is the slope of this line. And just so if you haven't learned calculus, a derivative is just a way of figuring out a slope at any point along a curve. So it's nothing too fancy. I'll see you in the next